Hello, I'm James Wilson from Colorado State University, and this is my talk on group isomorphism in nearly linear time for most orders for FOCS 2021. This is joint work with Heiko Dietrich of Monash University. First, a little bit of motivation, beginning with some outward motivation. I want to consider the question, where do we find in this, or in the API books, or even online, help with writing an equals? Now we know that this is necessary if we have a data type. This can't just be a container. At some level we need to allow for transformations between the states inside of them to do the right kinds of computations that we want. But there aren't dedicated APIs to equivalence testing the same way that there are to, say, sorting and searching and heaps and hashes and so forth. One of the ways that we can help lower that bar and make more access to such tools is to appreciate what's behind it. Now, I'm going to take a detour and talk about one of the techniques to relate a particular problem known as group isomorphism to this general equality question. And it starts by just looking at what equivalence even means. Equivalence has three rules: transitive, symmetric, and reflexive. If we just look at this transitive law, what it really is doing is taking a pair of evidences. Evidence, a computation that x is equivalent to y. Some computation verified that. And some computation verified that y was equivalent to z. We'd like to translate those two pieces of information into evidence that x is equivalent to z. And that's in a form of a product. The two pieces of evidence are multiplied by the transitive law, the transformation, into the new evidence. That turns out to be associative. And along with that, the other two axioms of an equivalence turn out to make what we know as a group. For example, here's the identity law given from the reflexivity. Reflexivity is that there's always a proof that x is transformable to itself. And if we put that into the transitive multiplication, we'd see that the reflexive law won't change the outcome of x equal to y. It just becomes x equal to y. It's behaving very much like an identity. And inverses come from the symmetric law. Evidence that x can be transformed into y turns into evidence that y transforms into x. And we can use that to think of it as loosely an inverse of that evidence. Now this is a little bit informal. It takes a type theory perspective to write this down with categories and so forth, but we just need to think of the big ideas here. And so it comes to, how do you actually deal with difficult examples of equality? One of the main examples comes back from 100 years ago. This was solved by Max Dane. It's called the Trefoil Knot problem. You can tie a simple knot hand over or the other way around, and they seem to be the same knot until you try to transform one to the other, and you can't find out how. Then the question is, are we just not creative, or is there really a reason? With difficult problems of equality, the first technique is to relax the conditions. Try not to study the entirety of the question, but study something weaker. Now this might actually permit these to become equivalent up to this weaker perspective, which is exactly what's happened here. Here what we have is we have a loop through the middle and a loop on each of these edges. If we loop around the three things, that'll be the same as having the big loop loop twice. But there is a left-hand and a right-hand orientation. So we keep track of that with having one have a positive 3 power and the other one have a minus 3. Now keeping track of that this was an equivalence relation, it means that we could record this information with two groups. These are known as the fundamental groups of complements of these knots. Given these two being the same, that's not surprising. We weaken the relationship. So now we start to enrich it. And instead of just comparing them as two equal groups, we add in extra information such as the crossing this way and that way, and under this enriched version, they're no longer equivalent. But we wouldn't have been able to see it so clearly if we'd asked that question at the beginning problem, going through an intermediate weaker problem and then checking the isomorphisms between the resulting groups became the information that we needed to do this in a practical way. It's an induction step. And it's probably for this reason that when we look at complexity classes, group isomorphism seems to appear in almost every single strata. Other problems certainly are equally important. For example, graph isomorphism is an important aspect of much of complexity theory. But what I mean to say is that if I look at graph isomorphism, one of the differences it has is that it's not heavily influenced by the type of input. A sparse graph versus a dense graph has roughly the same complexity for isomorphism. Meanwhile, if we take a multiplication table of an entire group versus generators and relations, we can find ourselves on an extreme from undecidable all the way down to nearly linear time. And this will be a talk about achieving nearly linear time in one of these models. So this is a good way to study complexity classes because we have one question that's not changing. It's always group isomorphism. And the only thing then that is actually influencing it is which data structures we have. So we're studying how the data structures influence the complexity rather than the particular problems. So let's look at an example of an isomorphism problem which is straightforward, though it wasn't when it was first discovered. This is known today as the Schrodingers Program. The idea here is that we might have some data that has a finite number of states that we're willing to exhaust. So what we need to know is whether we can get from one state to another using only the permitted transformations. For example, maybe we're only allowed to reverse list or to swap by 2's, or maybe it's something geometric like a Rubik's Cube that has only certain turns. We take those list of allowed permutations and call them X, and we take our 2 points omega and omega prime and we simply step out a transitive closure, walking every place that these generators X let us go. We will eventually reach omega prime. And when we do that, we not only have whether these two are equal, but we now have some infrastructure to check future ones by such as a spanning tree called a Schreier tree, and many other intermediate results. This has been the subject of much study, including by Sims, and later Knuth, and Jerome, and Jean Lux. And it'll be central to one of our algorithms. Now let's look at a hard problem where you can't write down all the states. This is string isomorphism. For example, I have the word eighth and height. And what we've done here is permuted the orders of the variables, but then we've also changed the alphabet. And that can be written down as a formula, which I would just look at the diagram for. I have the index set I is mapping to the alphabet sigma. That's my first string. And I compare it to a second string by applying a sequence of transformations G from I to I, and a sequence of transformations H from sigma to sigma, so long as they're allowable permutations. If I can find the pair GH that transforms one to the other, I've solved that string isomorphism problem. Naively, this is an n factorial search. So it's a bit surprised that this can actually be done in quasi-polynomial time, at least in the situation where the alphabet is fixed. This is the result that Lazzi Babai is famous for in graph isomorphism circles, and it's because string isomorphism is a harder problem than graph isomorphism and the one that is actually solved, or at least graph isomorphism reduces to it. I shouldn't say strictly harder. Let's investigate how that actually works a little bit so we can anticipate what should happen in the world of groups. The snapshot is that we started out with some very basic ideas that had some mathematical influence and interest. Then, by studying the specific problem of graphs, various techniques emerge. Some of them are local to global methods, to look inside the graph at certain pieces, removing some aspects, and see how they could be fused together. That's in color refinement type theory and was led by people like Weisfeld and Lehmann, and followed up by Babai, Erdos-Selko, and many others since then. Then there are structural techniques that try to say what is the quality that's being searched? How do you swap between these things? And that's the bounded valence approach of Lux. So this is a global approach and a local approach. If you glue them together, you can get a hybrid, which gives you an exponential improvement so that you have, instead of n factorial, you're down to simply exponential. But it didn't stop there. The analysis of this exponential had to have some cases that proved it was necessary. And the CFI graphs and various others like it soon emerged to demonstrate that there is a need to have some of these external tools because they don't simply cover the full landscape. When you have enough counterexamples to the methods that work, and you have enough analysis of the methods out there, you can eventually carve out a set of sub-cases that leave only a few options left. In the case of graphs, it was just the Johnson graphs that Babai was able to spot as the necessary additional techniques, combined with a lot of ingenuity. So now we'll try to do the same thing with isomorphism of groups, but we'll start with isomorphism tables, similar to strings, just in 2 dimensions. So now I have rows I, columns j, and then an alphabet sigma, and I want to permute all of these to make them equal, such as the 2 tables shown here. Already this is a version of string isomorphism with extra work because it has this extra coordinate set. But if we look to the complexity here, if we were to fix the alphabet sigma, we can do a little bit of work similar to Lux's hypergraph isomorphism. The idea in that situation was, while there are n factorial permutations to consider, there are only 2 to the n exponentially many, slightly less than n factorial, subsets to consider. If we look through the information in the subsets, we can make a simply exponential bound for hypergraph isomorphism. Carrying those ideas forward, Babai, Kodanotti, Grochow, and Chow were able to make a 2 to the n time isomorphism test for certain types of code equivalents, for example, when the alphabet is fixed. But now let's to the case that's still a bottleneck. This is when the alphabet is not fixed. In fact, it's the exact opposite extreme. It's when the alphabet is one of the index sets, and we'll make it square, I. Now this situation has a nice serendipity because when you have the same set repeated this way, you have what's known as a binary operation. It's a form of algebra. And the transformations that do this are now known as algebraic isomorphisms or homomorphisms. This allows you to research in a completely different field for ideas, and many of us have. The evolving methods look something like this. Early on, it was observed that, for example, with a few axioms, say that of a group or a quasi-group, Latin squares, many other properties, we can reduce the table to just a generating set. That way, when we need to compare, we just need to compare how many different generating sets there are. That offers an immediate bounding, provided the generators are few. And in many situations, they're logarithmic. Think of it as a Sudoku puzzle. You don't need many dots filled in before you're locked in. So once you have these generating set reductions, you get to quasi-polynomial time for many important families, such as groups. But that is still considered well below the threshold of expectation because, in some sense, you're still doing a brute force search, just over the information at this point. So we want to do better than that, and many people have. Three main techniques that I'll highlight certainly don't survey all the possibilities. One extreme is to take cases where the mathematics tells you that there's an extremely controlled situation, such as abelian groups, or on the other extreme, simple groups, non-abelian simple groups. In both cases, the way that the groups are built are forced by theory to have limitations. These limitations, when exploited with the proper data structures, lead to efficiencies. Then a second batch of techniques is to look for patches in the table that actually are vector spaces, and replace those patches in the table with efficient linear algebra. This is where adjoint tensor methods work. These techniques could now be combined, and have been, in a series of related and unrelated projects. For example, Babai and Chow have worked with the abelian methods together with the code equivalence methods of the semi-simplicity to create an abelian Silo Tower algorithm. Guo Chow and Chow have worked on combining them in a different way to create extensions of the semi-simple case. Myself and my co-author Heiko Dietrich have worked on cube-free. This is a form of color refinement in the sense that we're trying to look at diverse types of inputs and use modest amounts of information, such as how the order of the group breaks up, to do isomorphism testing by forcing the group theory in one direction. Color refinement properly for large prime powers, one of the most difficult examples, was solved by Li and Chow using some of these linearization methods of the adjoint tensor method. Along the way, we've also identified in several different communities exceptional cases that are proving that why certain techniques are in fact exponential or whatever their complexities are by identifying difficult sub-cases. This is work of my own, as well as Pascal Schweitzer, Guo Chow and Levitt, Brachter, and then various special one-off isomorphism tests used for local global analysis. We're by no means complete, but we are starting to see some of the same patterns that emerged in the solving of graph isomorphism. Fewer and fewer interesting cases are left. We're carving the landscape out. We're pointing to the direction of the difficult questions. So now let's get to the question at hand. How do we test isomorphism of most orders? And keep in mind, everything that I'll be doing here relates to a table of input, not generators and relations. Well, the basic idea is a divide and conquer. The simplest divide and conquer is probably the direct product. If I have a group formed by just coordinates, then I can look at the properties of A and B individually, somewhat in parallel. Now, there's some caveats there. These decompositions aren't in general unique, so you may need to adjust them by what's known as Kroll-Schmidt theory, and there's work established for doing that. Slightly more subtle, but equally enticing, is the concept of a semi-direct product. And this is a case where you have individualized components, A and B, but one of them influences the other. In this case, I have A twisting the multiplication in B. So we have to solve this in steps. First build A and deal with isomorphism of the A part, and then pass to B and make sure that we treat the twisting. It's more work, but it's a similar divide and conquer. Now, how do we know that we're going to steer ourselves into a situation where we can use such a divide and conquer? There could be many divide and conquers that are sort of not unique to the isomorphism type. They're just sporadic. So we'd like ones that we know we can guarantee are going to occur within this group or family of groups and be a reliable test for isomorphism. And one technique was given by Erdős and Palfy. They investigated the question purely for theoretical reasons of when does a group break up into a Cartesian product. and they observed an interesting addition to the factoring problem. We're all taught conventionally that a number n can be factored into a product of powers of primes, and we leave it at that. But you could actually go further and make a graph where each of the nodes are these powers of primes, and we put edges between them based on how one prime interacts with the other prime in the formula that's given here. That particular formula, specific to group theory, goes back to a technique known as CELO theory. But whatever the type of algebra it is, if there's interactions from that number theory that allow the group theory to exist, we can make a graph based on that. Doing so, they found that whenever you have these graphs, you get various connected components, and each connected component coordinatizes a direct factor. And this is unique, and so you can use this for a quick divide and conquer. Here's an example for a specific number n. It's the product of 3, 5, 7, and 17. 3 is connected to 7 because 3 divides 7 minus 1. So the CELO theory would allow me to make a group of order 21, which is perhaps interesting. But I can't, however, make a 5 and a 3 interact, nor a 5 and a 17, so those become direct factors. The trouble is, we want to be able to expand how many numbers n get to use this sort of trick. And already you can see that for an even number, because all other primes are odd, if there's an even number, the 2 is connected to everybody, one massive connected component. So it's somewhat feeble in terms of how many cases it applies to. So to broaden this, we brought in the type of decomposition. Not only do we put connected edges, we now make them oriented, and we expand them to the concept of hyperedges, which gets a more nuanced picture of how primes interact when building interesting group theory. We also take into account some of the details that are needed for exceptional behavior, like simple groups. That part we would just simply look up in the table. What this allows us to do is that from the connected components, the interconnected, the bidirectional connections in this hypergraph, we can split off a reliable, unique, semi-direct product decomposition. We do so in an abbreviated form in the abstract as listed. But here's an example of that for the specific number n 5,810,340. That factors into these primes. And we can see that on the left side, there's a cluster of small primes which are highly connected together. And then there are these two larger primes which are just wistfully connected to the number 2 and seem to ignore and are isolated from the rest. And just as the picture suggests, the proposition implies that such a group would break up as being a semi-direct product of this 2, 3, 5-bit, the 60 size group, and then products with these other primes. And nothing else can go on. And what's happening here is actually something that happens to most orders. What we actually have is the big clump of primes on one side, and then the disconnected primes. That makes hard group theory in the gray, and hard number theory in the blue. These are huge primes with discrete log problems. But we don't have to worry for our problem, because the number theory says that it's very rare for high delicate interactions to occur. So these are typically tiny numbers. And the group theory says that with lots of big primes, they don't interact in a way that's interesting, so they're cyclic groups. And so our divide and conquer can be done by brute force on each component. Now let's try to face a new problem within this. Along with creating these groups at this linear time, we've pushed the complexity down to the level of tables. It now becomes a problem of considering whether we knew it was a group in the first place. Many algebra problems don't need to worry about the promise hierarchy because the complexity of checking the identities is lower order. But at the level that we're at, we need to worry. Now there is work by Rajagopalan and Shulman that test identities of multiplication tables, such as associativity and group laws, and that's been done on a RAM model in nearly linear time. As we move to the complexities we're at, the scales we're at are trying to scale with large computations, where memory is now a problem. Communication costs have to be factored into our complexity, and there we have a blow-up. And so we need an improvement, which we've offered with a nearly linear time algorithm, which I'll walk through with an example. Suppose that I take this multiplication table, and I take the second row. That second row breaks up as a 6 cycle, and then I can simply see that that would only allow me to have 6 configurations, and that's not the size of the table, so this is not a group. It's not always that easy. Sometimes I get a table which does have a 5 cycle, but if I step out the multiplications, that 5 cycle does not agree with it being a group. So in summary, here we are. We can now test if something is a group in nearly linear time in a deterministic single tape Turing machine, and we can test isomorphism of groups of most orders in nearly linear time. Thank you.